What if everything you think you know about time and space is just the surface of something far stranger? Picture this. Right now, as you watch this video, time isn't ticking the same way for you as it is for someone on the other side of the planet, or even for a satellite orbiting Earth. That's the mind-bending reality of space-time, a cosmic fabric where the rules we take for granted bend, twist, and sometimes shatter entirely. And today, we're diving deep into 30 astonishing facts that'll make you question everything you thought you understood about the universe. From black holes that stretch time like taffy to mysterious wormholes that could theoretically teleport you across the cosmos in an instant, space-time isn't just the backdrop of our lives. It's an active, dynamic force shaping everything from the fate of galaxies to the ticking of your watch. And yet, most of us never stop to think about how utterly bizarre it all is. Why does time slow down when you move faster? How can space itself expand faster than light? These aren't just hypothetical puzzles, they're real phenomena that scientists grapple with every day, and they're proof that the universe is far weirder than our everyday experiences suggest. This video is your ticket to a journey through the most jaw-dropping, head-spinning corners of space-time. We'll explore how gravity warps time, why the past might not be as fixed as it seems, and whether parallel universes could be hiding just beyond the edge of our perception. And here's the best part, you don't need a physics degree to come along for the ride. Each fact is served up with clear explanations, vivid analogies, and a dash of cosmic wonder, because understanding the universe shouldn't feel like solving a riddle. So buckle up, by the time we're done, you'll never look at the clock or the night sky the same way again. Think of space-time like a giant cosmic trampoline, only instead of kids bouncing on it, there are planets, stars, and galaxies stretching its surface. This is Einstein's revolutionary idea. Space and time aren't separate things but woven together into a four-dimensional fabric. And just like a trampoline sags under the weight of a bowling ball, space-time bends around massive objects. That's gravity in action. The heavier the object, the deeper the dent, and the stronger its gravitational pull. Take our sun, for example. It's massive enough to warp the space-time around it, creating a sort of invisible valley that keeps Earth and the other planets orbiting. Without that curve, we just drift off into the void. But here's where it gets even wilder. Time itself is part of this fabric. Near a black hole where space-time bends to an extreme, time slows down dramatically. If you could hover near the edge of one, you'd age far slower than someone back on Earth. We even see this bending of space-time play out in everyday life, though on a much smaller scale. GPS satellites have to account for the fact that time ticks slightly faster for them up in orbit than it does for us on the ground, thanks to Earth's gravity warping space-time. Without those adjustments, your phone's navigation would be off by miles. So the next time you check a map or glance at the stars, remember, you're not just looking at empty space. You're seeing the invisible fabric of the universe itself, flexing and twisting under the weight of everything in it. Ever wonder why time doesn't just tick away at the same steady pace everywhere in the universe? It turns out the speed of time depends on where you're standing literally. The closer you are to something with enormous mass, like a planet or a black hole, the slower time moves for you compared to someone floating in empty space. This bizarre phenomenon is called gravitational time dilation, and it's not just science fiction, it's a fundamental part of how our universe works. Imagine you and a friend synchronize your watches, then your friend blasts off to orbit Earth while you stay on the ground. When they return, their watch will show slightly more time has passed than yours. Why? Because Earth's gravity creates a stronger dent in space-time at the surface, making time crawl just a tiny bit slower for you. The effect is minuscule in everyday life, but near something as massive as a black hole, the difference becomes extreme. An hour near the event horizon could mean years or even centuries passing elsewhere in the universe. This isn't just theoretical, engineers have to account for it every day. GPS satellites orbit high above Earth where gravity's grip is weaker, so their onboard clocks tick faster than those on the ground. If scientists didn't adjust for that difference, GPS locations would drift off by nearly 7 miles every single day. That's how real and measurable this effect is. The universe doesn't just bend space, it bends time itself, and the rules we take for granted down here don't always apply out there. So next time you check your phone for directions, remember, you're relying on the fact that time itself is flexible. Light doesn't just illuminate our world, it sets the ultimate speed limit for the entire universe. No matter how hard you try, nothing with mass can ever catch up to a beam of light. And this isn't just a rule, it's woven into the very fabric of space-time itself. Einstein's theory of relativity tells us that as an object approaches light speed, strange things start happening. Time stretches, distances shrink, and the energy needed to go even a fraction faster becomes infinite. That's why particles in giant accelerators like the Large Hadron Collider can get painfully close to light speed but never quite reach it. But here's where it gets truly mind-bending. Light speed isn't just a barrier for movement, it's a boundary for time. Imagine two astronauts, one staying on Earth and the other blasting off at nearly light speed. When the traveling twin returns, they'd find their Earth-bound sibling has aged far more than they have. That's the famous twin paradox, and it's not just a thought experiment. Atomic clocks flown on jets and satellites have confirmed it. Time literally slows down the faster you go. Why does this happen? Because space and time are two sides of the same coin. As you approach light speed, your motion through space eats into your motion through time like a cosmic trade-off. The universe enforces this rule so strictly that if you could somehow hit light speed, time would stop altogether. Photons, the particles of light, experience no time at all from their own perspective. A trip across the galaxy happens in an instant for them. This cosmic speed limit also creates some baffling paradoxes. If you could somehow break it, you'd violate causality, meaning you could arrive before you left, turning cause and effect into nonsense. That's why the universe slams the door on faster than light travel, not out of spite, but to keep reality from unraveling. So next time you flick on a light switch, remember those photons racing to your eyes are playing by rules that shape everything from atoms to galaxies. And those rules ensure the universe stays logical, even when its consequences seem anything but. What if you could walk through a door and instantly emerge on the other side of the galaxy? That's the tantalizing promise of wormholes, cosmic shortcuts that could bend space-time so dramatically they'd turn a million-year journey into a quick stroll. These hypothetical tunnels, known as Einstein-Rosen bridges, aren't just science fiction. They're a legitimate, though wildly speculative, consequence of Einstein's equations. Picture space-time as a sheet of paper folded in half. A wormhole would be like poking a pencil through the fold, connecting two distant points in an instant. The math suggests wormholes could exist, but there's a catch. They'd likely be incredibly unstable, without some exotic form of matter, something with negative energy to prop them open. These tunnels would snap shut faster than you could blink, crushing anything inside. That's why films like Interstellar imagine advanced civilizations or futuristic technology stabilizing them. But here's the wild part. If wormholes could be tamed, they wouldn't just bridge space. They might also connect different times. Step in one end today, and you could emerge centuries in the past or future. Of course, the universe seems to guard these shortcuts fiercely. No natural wormholes have ever been observed, and the energy required to create or stabilize one is beyond anything we can fathom. Yet the mere possibility shakes our understanding of reality. Could wormholes explain bizarre cosmic phenomena we haven't even identified yet? Might they be the key to unlocking faster than light travel without breaking physics? For now, they remain a thrilling what if, a reminder that the universe's rulebook might have pages we haven't even glimpsed. Black holes don't just bend space-time, they shred the rulebook entirely. Imagine tossing a bowling ball onto that cosmic trampoline we talked about earlier, but this time the ball is so heavy it punches a hole straight through the fabric. That's essentially what a black hole does to space-time. Its gravity is so intense that near its edge, known as the event horizon, the very laws of physics as we know them start to unravel. Cross that boundary and there's no turning back. Not even light can escape, but the real nightmare begins long before you reach the event horizon. Picture this: you're falling feet first toward a black hole. The gravitational pull on your feet is exponentially stronger than on your head, stretching you like taffy in a process gruesomely nicknamed spaghettification. Your body would be torn apart molecule by molecule, transformed into a stream of particles spiraling into oblivion. Even if you could survive the stretching, time itself would warp so drastically that seconds for you could equate to years for someone watching from a safe distance. And here's where it gets even stranger. At the black hole's core lies the singularity, a point where space-time curves infinitely and all known physics breaks down. It's a place where matter is crushed into a space smaller than an atom, where density becomes meaningless, and where the very concepts of here and now cease to apply. Scientists still grapple with what truly happens inside a singularity, because our current equations spit out infinity's cosmic error messages hinting that we're missing a deeper theory. Yet black holes aren't just cosmic destroyers, they're also laboratories for the most extreme physics imaginable. Their intense gravity can lens light from objects behind them, creating eerie rings or multiple images in the sky. They emit faint radiation, dubbed Hawking radiation, slowly evaporating over eons. And when two black holes collide, they send ripples through space-time itself, gravitational waves we can now detect here on Earth. These phenomena remind us that even in the universe's most violent corners, there's a twisted order, a reminder that space-time isn't just a stage for the cosmos, but a participant in its most dramatic performances. Here's something that sounds impossible but is absolutely real. The universe is expanding faster than light. And no, that doesn't break Einstein's cosmic speed limit, because it's not objects moving through space, but space itself stretching apart. This is metric expansion, the force that's been pushing galaxies away from each other since the Big Bang. Picture a loaf of raisin bread baking in the oven. As the dough rises, every raisin moves farther away from every other raisin, not because they're traveling, but because the space between them is growing. Now imagine two raisins so far apart that the dough between them stretches faster than light speed. That's exactly what's happening with distant galaxies. The farther apart they are, the faster space expands between them. At some distance known as the Hubble horizon, this expansion hits light speed, making galaxies beyond it forever invisible to us. Their light will never reach Earth because the space it must cross is growing too fast. And it gets weirder. Over time, even nearby galaxies will cross this horizon, vanishing from our cosmic view as the expansion accelerates. But how does this not violate relativity? Because nothing is actually moving through space faster than light. Space itself is the thing stretching. Think of it like ants on a rubber band. If two ants crawl toward each other while someone stretches the band, their progress slows even though they haven't changed speed. Now imagine that rubber band stretching so fast the ants can never meet, even if they sprint at top speed. That's the universe's expansion in a nutshell. Space isn't just a stage, it's an active player rewriting the rules of distance itself. This expansion isn't uniform, though. Nearby, gravity holds galaxies together against the stretch, like raisins clustered in the dough. But on cosmic scales, dark energy, the mysterious force driving the acceleration, wins out, flinging galaxies apart. The result, a future where distant galaxies fade into darkness, leaving only our local group behind in an ever-expanding void. So while nothing can outtrace light within space, space itself has no such limits. It's the ultimate cosmic loophole, one that ensures the universe will forever keep parts of its story just out of reach. time travel isn't just a sci-fi fantasy, it's a real, measurable phenomenon, at least when it comes to jumping forward. Thanks to Einstein's theory of relativity, we know that the faster you move or the stronger the gravity you're in, the slower time passes for you compared to someone else. This isn't speculation, it's been tested with atomic clocks so precise they can detect the slightest distortions in time. Take the Hayfel-Keating experiment in the early 1970s. Scientists flew atomic clocks around the world on commercial jets, then compared them to clocks left on the ground. Sure enough, the traveling clocks ran slightly slower, proving that motion literally steals time from you. Now imagine cranking that effect up to extremes. If you could build a spaceship that travels close to light speed, a few years of ship time could mean centuries passing on Earth. Your journey would feel like a quick trip, but you'd return to a planet where everyone you knew had aged decades or disappeared entirely. The same thing happens near a black hole's event horizon, where gravity warps time into a crawl. Spend an hour skirting the edge, and years could vanish elsewhere in the universe. In both cases, you're not breaking any laws of physics, you're just riding the natural curves of space-time. The strangest part, this isn't just theoretical. Astronauts on the International Space Station experience it on a tiny scale. Because they're moving faster and experiencing weaker gravity than us on Earth, they age about 0.0005 seconds less every year. It's a minuscule difference, but it proves the principle. Time is flexible, and with the right conditions, the future is just a destination you can reach faster than everyone else. So while we can't yet build a light-speed engine or survive a black hole encounter, the science is clear. The universe doesn't have a single, universal clock ticking for everyone. Time is personal, shaped by speed and gravity, and that means the path to tomorrow might just be a matter of finding the right cosmic shortcut. What if the past isn't gone and the future isn't unwritten? According to the block universe theory, every moment from the Big Bang to the distant future exists simultaneously, frozen in a vast four-dimensional tapestry. Think of it like a DVD where every scene is already encoded, but your consciousness is the laser moving through it, creating the illusion of a flowing present. This radical idea comes straight from Einstein's own writings, where he described the distinction between past, present, and future as merely an illusion. In this view, time isn't a river carrying us forward. It's more like a landscape where every event, from your birth to the heat-death of the universe, sits permanently in its designated coordinates. Just as you can pinpoint a location in space with latitude and longitude, events have a when as fixed as their where, the sensation of time passing. That's just your brain stitching together these frozen slices, like flipping through a flipbook. Here's where it gets trippy. If the block universe is real, your future self already exists somewhere in the cosmic ledger. That first kiss, your last breath, the moment humans land on Mars, they're all equally real, just elsewhere. Even your perception of making choices could be an illusion, like a character in a novel believing they're acting freely when every word was predetermined. Scientists don't all agree on this interpretation, but it solves bizarre physics puzzles. For instance, quantum entanglement, where particles instantly influence each other across vast distances, makes perfect sense if their connection exists outside time. And relativistic effects like time slowing near black holes fit neatly into this frozen framework where now is relative. Yet the block universe raises haunting questions. If everything is predetermined, does free will evaporate? Or is free will just us experiencing the path our four-dimensional selves already occupy? Some philosophers argue this doesn't rob life of meaning. It simply means the meaning was always there, woven into the fabric of reality itself. So next time you glance at old photos or dream about tomorrow, consider this. They might not be memories or fantasies, but destinations on a map where every moment is eternally present. If you think teleportation belongs only in sci-fi, Think again, quantum particles do it every day. At the subatomic level, particles can vanish from one location and reappear in another without crossing the space in between, a phenomenon called quantum tunneling. But even stranger is quantum entanglement, where two particles become mysteriously linked, instantly influencing each other no matter how far apart they are. Einstein famously called this spooky action at a distance because it defies everything classical physics taught us about how the universe should work. Here's how it breaks the rules. Imagine you have a pair of entangled particles, say, electrons flipped in opposite directions. Separate them by a light year, and the moment you measure one spin, the other instantly snaps into the opposite state. No signal passes between them, no force travels through space. The change happens faster than light, as if the particles share an invisible connection that ignores distance entirely. This isn't just theory. Experiments have confirmed it repeatedly, with particles separated by hundreds of miles still behaving as if they're a single entity. What does this mean for space-time? It suggests that at the quantum level, the fabric of reality might not be as local as we thought. In our everyday experience, objects influence each other by bumping into things or sending signals through space. But entangled particles seem to bypass space-time altogether, operating on a deeper, non-local layer of reality. Some physicists speculate this could hint at a hidden dimension or a more fundamental structure beneath space-time, one where here and there aren't rigidly separate. The implications are staggering. If particles can coordinate instantly across cosmic distances, could we one day harness this for communication or even teleportation? Scientists have already teleported quantum states between particles in labs, though scaling this up to humans remains pure fantasy for now. But the mere fact that particles break the speed of light rule without actually violating relativity, since no information is transmitted, forces us to rethink what space-time truly is. Maybe it's not the rigid stage we imagine, but something far more fluid, where separations are illusions and connections run deeper than distance. So next time you hear about quantum weirdness, remember, the universe isn't just stranger than we think. It's stranger than we can think, and every experiment peels back another layer of the mystery. You might think a vacuum is just empty space, nothing there, just pure stillness. But the universe has a way of laughing at our assumptions. What we call empty is actually a seething, bubbling quantum foam, where particles flicker in and out of existence so fast they defy the very notion of nothingness. These are virtual particles, short-lived pairs of matter and antimatter that appear spontaneously, borrow energy from the void, then annihilate each other almost instantly. It's like the cosmos is running a relentless slot machine where every pull of the lever creates something from nothing, even if only for a fraction of a second. This isn't just theoretical. We've seen the effects of this quantum frenzy in experiments like the Casimir effect. Place two uncharged metal plates extremely close together in a vacuum, and they'll inexplicably push toward each other. Why? Because the space outside the plates has more room for virtual particles to pop up, creating a pressure differential that nudges them together. The empty space between them isn't empty at all, it's a storm of activity, with particles flaring into existence and vanishing faster than the blink of an eye. Now imagine this chaos happening near the edge of a black hole. Here's where things get wild. If a virtual particle pair appears right at the event horizon, one might fall in while the other escapes. The escaping particle becomes real, stealing a tiny bit of the black hole's energy to pay its debt to the universe. This is Hawking radiation, the slow leak that causes black holes to evaporate over eons. That's right, even the darkest, most destructive objects in the cosmos are slowly fading away, thanks to the restless energy of empty space. What does this mean for our understanding of reality? It shatters the idea that nothingness is passive. The vacuum of space is more like an invisible ocean, its surface calm but its depths teeming with unseen activity. Every cubic centimeter of the universe, from the void between galaxies to the air around you, is a whirlwind of potential where particles dance on the edge of existence. So the next time you gaze at the night sky, remember, the real magic isn't just in the stars, it's in the seemingly empty spaces between them, where the fabric of reality itself is alive with possibility. The Big Bang didn't just birth our universe, it might have spawned countless others, each with its own bizarre set of physical laws. This is the multiverse hypothesis, where our cosmos is just one bubble in an infinite froth of parallel realities. Picture a pot of boiling water where every rising bubble represents an entire universe, some with stronger gravity, others where light moves slower or where time itself flows backward. These cosmic bubbles aren't science fiction. They emerge naturally from the math of inflationary theory, which describes how space expanded faster than light in the universe's first fraction of a second. In this scenario, inflation never truly stops, it just pauses in certain regions, forming stable pockets like ours while continuing indefinitely elsewhere. Each pause creates a new universe with random physical constants, meaning somewhere out there, a version of reality might have stars that burn in shades we can't comprehend or atoms that assemble into impossible structures. Some universes might collapse instantly, while others could harbor life forms made of dark matter. The unsettling truth, we'll never see them. These bubble universes are forever beyond our cosmic horizon, racing away as space itself expands faster than light can bridge the gap. Yet the evidence might be hiding in plain sight. If two bubbles collided early in cosmic history, the crash could have left scars in the cosmic microwave background, the afterglow of the Big Bang. Scientists have scanned this ancient light for odd temperature patterns, though no definitive bruise has been found. Another clue could come from gravitational waves, ripples in space-time that might carry echoes of neighboring universes brushing against ours. The multiverse idea solves baffling mysteries, like why our universe's constants seem fine-tuned for life. If infinite variations exist, it's no surprise we find ourselves in one where physics allows galaxies and biology. But critics argue it's untestable, more philosophy than science. After all, if we can't observe these other worlds, does the theory even count as physics? Whether real or just a provocative thought experiment, the multiverse forces us to confront the sheer strangeness of existence. Our universe might not be the main event, just a single page in an endless cosmic library where every possible reality already exists, written into the fabric of space-time itself. Here's something truly mind-bending to think about the next time you stand up. Your head is technically aging faster than your feet. Not by much, just a few billionths of a second over a lifetime, but this isn't science fiction. It's the direct result of gravity's grip on space-time, and it means time itself flows at slightly different rates depending on how close you are to Earth's center. Picture gravity as a force that doesn't just pull uniformly, it tugs harder the closer you are to its source. That means your feet, being a couple of feet nearer to Earth's core, experience a smidge stronger gravity than your head. According to Einstein's general relativity, this tiny difference in gravitational strength translates to a minuscule difference in how fast time passes. For every second that ticks by at your feet, your head experiences a fraction of a second more. Over decades, this adds up. By the time you're 80 years old, your head will be about 90 billionths of a second older than your feet. This effect, called gravitational time dilation, has been measured with astonishing precision. Atomic clocks placed just a foot apart in elevation show measurable differences. Higher clocks tick faster because they're farther from Earth's gravitational pull. Even your upstairs and downstairs clocks drift out of sync over time, though you'd need instruments far more sensitive than your watch to notice. What's wild is that this isn't some abstract quirk of physics, it's woven into the fabric of daily life. GPS satellites orbiting 12,000 miles above Earth have to account for this effect in reverse. Their clocks run faster than those on the ground because they're in weaker gravity, And if engineers didn't adjust for this, navigation systems would be off by miles within minutes. So while the difference between your head and feet is too small to matter in practice, it's proof that time isn't some universal metronome. It's a fluid, personal experience shaped by where you are and how you're moving. And here's the real kicker: this gradient exists everywhere gravity does. On a neutron star where gravity is billions of times stronger than Earth's, the difference between your head and feet wouldn't just be nanoseconds, it could be years. Your feet would age slower, crushed under the weight of extreme space-time curvature, while your head races ahead in time. It's a reminder that even the most ordinary actions, like standing up or climbing stairs, are quietly bending the rules of reality in ways we're only beginning to understand. Every star you see at night is a postcard from the past, stamped with the date it left its source and began traveling toward your eyes, that shimmering glow from Orion's belt. It embarked on its journey to Earth around 1400 years ago, around the time humans were first navigating by the stars. Even our closest stellar neighbor, Proxima Centauri, sends light that's over 4 years old by the time it reaches us. And the Andromeda Galaxy, those swirling arms we admire through telescopes, left their home 2.5 million years ago, before early humans had even discovered fire. This isn't just poetic coincidence, it's the ironclad rule of our universe. Light moves fast, but space is vaster. At 300,000 kilometers per second, a beam could circle Earth 7 times in the blink of an eye. Yet across cosmic distances, even that speed becomes sluggish. The sunlight warming your skin, it's already 8 minutes old when it arrives. If the sun suddenly vanished, we wouldn't know until those final rays finished their delayed delivery. What's truly humbling is realizing that every telescope is, in effect, a time machine. When astronomers peer at galaxies billions of light years away, they're glimpsing the universe as it existed before Earth formed. The James Webb Space Telescope's deepest images capture galaxies whose light has traveled over 13 billion years, showing them as infants in a cosmos still fresh from the Big Bang. We're not just observers of space, we're archaeologists of time, piecing together cosmic history one photon at a time. This delay creates bizarre paradoxes. Right now, a civilization in Andromeda could be pointing telescopes at Earth and seeing woolly mammoths roaming the plains. They'd have no way of knowing humans exist until their light catches up millions of years from now. Similarly, aliens 50 light-years away might currently be detecting our first television broadcasts, episodes of I Love Lucy, just now reaching their distant world. The deeper implication: the universe we perceive is an illusion of stacked timelines. The stars in your night sky aren't just separated by space, but by epochs. That constellation you're admiring might already be gone, its light still traveling toward us like a final message from a ghost. So every time you look up, remember, you're not just seeing space. You're reading a library of light where every shelf holds a different chapter of cosmic history. Deep within the fabric of the universe, there might be invisible threads, flaws in space-time itself, left over from the cosmic forge of the Big Bang. These are cosmic strings, hypothetical one-dimensional defects thinner than a proton but stretching across the entire universe, carrying unimaginable density. Picture them like cracks in a frozen lake, remnants of a phase transition when the early universe cooled from a seething plasma into the structured reality we know. But unlike ordinary cracks, these don't just sit there. They warp space-time around them with such intensity they could bend light, distort time, or even stitch closed loops into reality itself. If a cosmic string passed through your room, you wouldn't see it, but its gravitational fingerprint would be unmistakable. Light from objects behind it would split into mirrored images, as if space itself had become a funhouse lens. Even stranger, two parallel strings moving past each other could twist space-time into a closed time-like curve, a fancy term for a time loop. Hypothetically, circling them in just the right way might let you return to your starting point before you left. It's not quite a time machine, but it's the closest thing physics currently allows without breaking causality. What makes these strings so bizarre is their scale. A single cosmic string just a kilometer long might weigh as much as an entire mountain, yet its width would be smaller than an atom. That extreme density means they'd vibrate like guitar strings plucked by the cosmos, sending gravitational waves rippling across the universe. Some scientists speculate these vibrations could explain odd quirks in the cosmic microwave background, or even seed the formation of galaxies by clumping matter around their gravitational shadows. The wildest part, we might have already detected them indirectly. Strange double images of distant quasars perfectly mirrored could be the signature of a string warping light along its path. And if two strings ever crossed, their collision would release a burst of gravitational waves detectable by observatories like LIGO. So while they remain hypothetical, cosmic strings aren't just mathematical curiosities, they're potential keys to understanding the universe's most tangled mysteries. Whether time loops, gravitational lenses, or relics of the Big Bang, cosmic strings remind us that space-time isn't just a smooth canvas. It might be more like a pane of glass, fragile and flawed, bearing scars from its violent birth, hidden in plain sight. Every moment of your life feels like it's flowing in one direction, from past to future, but the universe might be playing an elaborate trick on you. At the deepest level, the laws of physics don't actually care which way time moves. Newton's equations, Einstein's relativity, even quantum mechanics work perfectly whether time runs forward or backward. Flip the sign in the math and the universe keeps humming along. So why can't you unburn a piece of toast or uncry spilled milk? The answer lies in a single, slippery concept: entropy, the universe's relentless march toward disorder. Think of entropy as the cosmic equivalent of your bedroom. It starts neat, but over time, clothes pile up, dust settles, and chaos creeps in. The same thing happens to the entire universe. Energy spreads out, systems unravel, and complexity decays. This one-way slide from order to chaos is the only reason we experience time as having a direction at all. Without entropy, every moment would be indistinguishable from the next, like frames of a movie played in reverse or a deck of cards endlessly reshuffled into perfect order. But here's the puzzle. If physics is time-symmetric, if the equations work just as well backward, why isn't the universe a static, timeless blob? Some theorists argue the Big Bang holds the key. Our universe began in an improbably low entropy state, like an egg balanced perfectly on its end. From that moment, the egg had to tip, setting the arrow of time in motion. But that just pushes the mystery deeper. Why was the early universe so ordered? Was it pure chance, or a clue that time's arrow is just a local phenomenon? A quirk of our cosmic bubble in a multiverse where other universes might run backward. The debate gets even stranger when you consider quantum mechanics. At the subatomic level, particles don't always play by entropy's rules. Quantum systems can unscramble themselves, seemingly reversing time's arrow. Experiments with entangled particles show correlations that appear to defy cause and effect, as if future events influence the past. Some interpretations, like the retrocausal theory, suggest time might flow both ways at the quantum scale, with our macroscopic experience of forward time emerging from the statistical noise of countless particles. So is time's arrow fundamental, or just an emergent illusion? The answer could reshape everything from cosmology to consciousness. If time's flow isn't inherent to reality but a side effect of entropy, then the past and future might be equally real, frozen in the block universe, with our perception of movement just a trick of the mind. Or perhaps entropy isn't the full story. Some physicists speculate that dark energy's accelerating expansion of the universe might eventually reverse entropy's grip, leading to a big crunch where time itself runs backward. For now, all we know is this: the universe keeps meticulous receipts. Every shattered glass, every gray hair, every dying star is a receipt stamped with entropy's irreversible signature. And yet, beneath it all, the equations whisper a tantalizing secret. Time's arrow might not be written into the fabric of reality, just etched into the way we experience it. So the next time you mourn the past or dread the future, remember, the universe in its deepest laws feels no such bias. It's only our place in the chaos that makes time's flow feel so absolute. Dark energy isn't just pushing galaxies apart. It might be writing the universe's most violent final chapter. Picture this, an invisible force stronger than gravity itself, accelerating the expansion of space until it overpowers every bond in existence. First, galaxies would vanish over the cosmic horizon, disappearing from view as space stretches faster than light can bridge the gap. Then, stars within surviving galaxies would drift apart, their gravitational ties severed. Eventually, planets would unravel from their orbits, followed by something even more horrific, the fabric of space-time itself tearing at the seams. This isn't science fiction. It's the Big Rip, one of cosmology's most chilling doomsday scenarios. What makes dark energy so dangerous is its potential to grow stronger over time. Right now, it accounts for roughly 70% of the universe's energy density, acting as a sort of anti-gravity that pushes space apart. But if this energy isn't constant, if it's a phantom field that intensifies as the universe expands, then its grip could become unstoppable. In this nightmare scenario, the acceleration wouldn't just separate galaxies, it would amplify until it rips apart everything. Solar systems would be shredded first, then planets, then molecules, and finally atoms themselves. Even the space between particles would stretch until the fundamental forces, gravity, electromagnetism, can no longer hold matter together, the timeline. Some models suggest this catastrophe could unfold in as little as 22 billion years. For context, that's roughly 5 times the current age of the universe. But the countdown wouldn't be gradual. In the final moments, expansion would spike so violently that the last stars, black holes, and even atomic nuclei would disintegrate in a cosmic flash. Space-time, the very stage of reality, would fracture into meaningless bubbles, each isolated and barren. No light, no structure, no physics as we know it, just an endless, seething void where the concept of here and now loses all meaning. Strangely, this apocalypse wouldn't break the speed of light. Instead, space itself would stretch so fast that objects wouldn't move through space. They'd be carried away by its expansion, like debris on a rubber band snapped at light speed. And unlike black holes or heat death, there's no escape. No technology could outrun this fate because the destruction wouldn't come from outside. It would emerge from the fabric of reality itself, rewriting the rules until nothing remained. Yet the Big Rip isn't certain. Observations of distant supernova and galaxy clusters suggest dark energy's strength might be constant, a cosmological constant, as Einstein once proposed. If so, the universe will still end, but in a slower, colder demise, the heat death, where expansion dilutes all energy into a silent, eternal dark. But if dark energy is phantom, if it grows stronger, then the universe's finale won't be a whisper. It'll be a scream. The eerie part, we may already have clues. Astronomers are racing to measure dark energy's equation of state, a technical term for how its pressure relates to its density. If the numbers skew toward phantom energy, the Big Rip moves from speculative to plausible. Upcoming telescopes like the Vera C. Rubin Observatory could deliver answers within decades, peering into the cosmic acceleration with unprecedented precision. So while the Big Rip remains a hypothesis, it forces us to confront a profound truth. The universe isn't just expanding, it's evolving, and its fate hinges on mysteries we're only beginning to unravel. Whether it ends in fire, ice, or the ultimate unraveling of space-time, one thing's clear: dark energy holds the pen, and we're just reading the story as it's written. Here's something you've never felt but is absolutely true. Right now, you're hurtling through the cosmos at the speed of light, not through space but through time. Einstein's relativity reveals a mind-blowing secret. Every object in the universe is always moving through the four-dimensional fabric of space-time at exactly light speed. The only difference is how that motion gets divided between the three dimensions of space and the one dimension of time. Think of it like a cosmic speedometer stuck at light speed, with a slider allocating your velocity between space and time. When you're sitting still, like you are right now, all your motion is directed through time. That's why seconds tick by at their normal rate. But the moment you start moving through space, say, walking to the fridge or riding in a car, you're stealing a tiny fraction of that speed from time and giving it to space. The faster you move spatially, the slower your clock runs, because your total speed through space-time must always add up to light speed. This explains why astronauts on the International Space Station age slightly slower than people on Earth. They're traveling at nearly 17,000 miles per hour, which means more of their light speed budget gets spent moving through space, leaving less for time. The effect is minuscule, just microseconds per year, but it's measurable proof that motion through space literally borrows from motion through time. Now imagine cranking this effect to the extreme. If you could somehow reach light speed through space like a photon, your entire velocity would be allocated to space, leaving none for time. From the photon's perspective, its journey across the universe happens in an instant, no matter how many light years it travels. Time doesn't pass for light because it's spending all its cosmic speed on spatial movement. This also reveals why nothing can accelerate past light speed. As you approach it, more of your motion shifts to space, making time slow to a crawl. To exceed light speed would require stealing more from time than exists, like trying to fill a cup that's already empty. The universe enforces this balance ruthlessly, ensuring the sum of space and time motion never exceeds light speed. So the next time you glance at a clock, remember, its ticks aren't just marking time. They're proof you're surfing the universe's ultimate speed limit, a fixed velocity through reality itself, forever trading moments for movement in an unbreakable cosmic bargain. If black holes are the universe's ultimate garbage disposals, sucking in everything that crosses their path, then white holes are their bizarre, time-flipped twins. Imagine a cosmic fire hose blasting matter outward with such force that nothing can enter, reversing the rules of a black hole entirely. This isn't just sci-fi whimsy, it's a serious mathematical prediction emerging straight from Einstein's equations. While black holes trap even light, white holes would repel it, spewing out energy and particles in a violent burst that defies gravity's pull. The catch: no one's ever seen one. The idea of white holes arises from playing with the math of general relativity. Just as you can rewind a video to see events in reverse, physicists can theoretically flip the equations describing black holes to imagine these cosmic geysers. Some theories suggest white holes could be the other end of a black hole's tunnel, a wormhole exit where matter swallowed by a black hole gets regurgitated somewhere else in space or time. Others propose they might be remnants of black holes that have evaporated through Hawking radiation, exploding in their final moments like a deflating balloon with all its pent-up energy suddenly released. But why haven't we spotted one? For starters, white holes would be outrageously unstable. Unlike black holes, which form naturally from collapsing stars, white holes would require absurdly precise conditions to exist, like a universe finely tuned to birth them. Any speck of dust or wandering atom trying to enter would destabilize them, causing an instantaneous collapse into a black hole. Plus, their violent outbursts would likely resemble other cosmic explosions like supernova or gamma-ray bursts, making them easy to miss in the cosmic noise. The most tantalizing possibility: white holes might explain mysterious flashes of energy we've already detected. Some physicists speculate that fast radio bursts, intense, millisecond-long pulses of radio waves from deep space, could be white holes flickering into existence and vanishing just as quickly. Others wonder if the Big Bang itself was a white hole event, with our universe erupting from a singularity in another cosmos. Of course, skeptics argue white holes are just mathematical curiosities with no basis in reality. After all, if they defy entropy by spewing out ordered energy without an obvious source, they'd violate thermodynamics unless they're connected to black holes in some hidden way. Until we find concrete evidence, white holes remain a ghost in the equations, haunting the edges of physics with their paradoxical allure. Whether cosmic myths or hidden realities, white holes challenge our understanding of space-time's flexibility. They whisper that the universe might not just bend the rules, it could sometimes run them backward, and if we ever do find one, it would rewrite not just astrophysics textbooks, but our very notion of cause and effect in the cosmos. On September 14, 2015, a ripple in space-time so faint it stretched a 4-kilometer laser beam by less than 1/10,000th, the width of a proton, reached Earth after traveling 1.3 billion light-years. This wasn't just any cosmic tremor, it was the death cry of two black holes, each roughly 30 times the mass of our Sun, spiraling into each other at half the speed of light before merging into a single, more massive void. The event released more energy in gravitational waves than all the stars in the observable universe combined, and for the first time in history, humanity caught the echo. This monumental detection by LIGO, the Laser Interferometer Gravitational Wave Observatory, didn't just confirm Einstein's century-old prediction. It proved that space-time isn't just a static stage, it's a dynamic fabric that can stretch, compress, and ring like a drumhead struck by the universe's most violent events. Picture tossing two pebbles into a pond. The ripples they create as they sink spread outward, warping the water's surface. Colliding black holes do the same to space-time, sending distortions rippling across the cosmos at light speed. But unlike water waves, these gravitational ripples don't need a medium to travel through. They are the warping of space and time itself. LIGO achievement was akin to measuring the distance between Earth and Alpha Centauri, 4.3 light-years, down to the width of a human hair. The observatory's twin detectors, separated by 3,000 kilometers, use lasers bouncing between mirrors to spot infinitesimal stretches in space-time as waves pass through. When the signal from those colliding black holes arrived, it matched Einstein's equations with stunning precision, down to the millisecond. The black hole's final orbits before merging reached frequencies we could almost hear, a rising chirp in the audio translation, ending in a defining thud as they became one. Since that first detection, LIGO and its European counterpart, Virgo, have caught dozens more gravitational wave events, not just black hole mergers, but neutron stars colliding in fiery kilonovae that also light up the sky in gamma rays and heavy elements like gold. Each detection paints space-time as something more fluid than we ever imagined. Some waves might even carry echoes from cosmic strings or primordial black holes, relics of the Big Bang. The implications are staggering. Gravitational waves let us hear the universe in a way light never could. Black holes, invisible to telescopes, reveal themselves through these vibrations. Neutron star crashes, hidden behind dust clouds, broadcast their collisions in ripples we can now decode. It's as if the cosmos handed us a new sense, one that peers past obscuring gas and darkness to the hidden symphonies of warping space. And we're just tuning in. Future detectors like the space-based LISA mission will catch lower frequency waves from supermassive black holes merging at the hearts of galaxies. Others might spot the cosmic gravitational wave background, the faint hum from countless collisions over billions of years. With each new detection, we're not just observing the universe. We're feeling its very fabric vibrate, learning to read the stories written in space-time's trembling hand. Light doesn't just travel at the universe's speed limit, it experiences something far stranger, the complete absence of time. From a photon's perspective, the moment it's emitted to the moment it's absorbed stretches exactly 0 seconds, no matter how many billions of light years it crosses. That means if you could hitch a ride on a beam of light from a distant quasar, your entire journey across the cosmos would feel instantaneous, like flipping a switch and arriving before your finger even left the button. This mind-bending reality comes straight from Einstein's theory of relativity. As objects approach light speed, time slows down for them relative to the outside world. But photons don't just move at light speed, they are light speed, which means time doesn't just slow down for them. It stops entirely. Their clock never ticks, their internal experience never progresses. The 14 billion-year lifespan of the universe, to a photon created at the Big Bang and absorbed by your eye today, those eons passed in less than the blink of a thought. This isn't just theoretical wordplay. We see this effect in cosmic rays particles accelerated to nearly light speed by supernova or black holes. Muons, a type of cosmic ray particle, should decay long before reaching Earth's surface based on their natural lifespan. Yet because they're moving so close to light speed, their clocks run so slowly that they survive the trip. For the muon, the journey might feel like microseconds, while Earth-bound observers measure it as thousands of years. Light takes this to the extreme: zero time, zero decay, zero aging. The implications rewrite how we think about distance and existence, that starlight you see tonight. For the photon, there's no tonight. It didn't experience the centuries it spent traveling. The Andromeda Galaxy's light, 2.5 million years old by our clocks, didn't age a picosecond from its own perspective. This duality, where time is both endless and non-existent, shows just how flexible reality becomes at light speed. And here's the cosmic punchline: this isn't unique to light. Any massless particle, like gluons or gravitational waves, would experience the same timelessness. Even the gravitational ripples from colliding black holes racing toward us at light speed don't experience their journey. They're frozen moments stretched across space, their entire existence compressed into a single instant. So next time you bask in sunlight, remember, those photons didn't spend 8 minutes traveling from the sun to your skin. From their viewpoint, they were created and destroyed in the same timeless flash, proof that the universe's speed limit isn't just about movement. It's about tearing the very fabric of time itself. What if everything you see, the stars, galaxies, and even your own hands, is just a projection, like a movie playing on the surface of an invisible cosmic screen? This wild idea isn't science fiction, it's the holographic principle, a theory suggesting our three-dimensional universe might actually be encoded on a two-dimensional surface, like data etched onto a DVD. Imagine your entire life, from the taste of coffee to the vastness of space, existing as nothing more than vibrations on a distant, flat boundary. Sound impossible? The math behind black holes hints that this might not just be possible, it could be fundamental to how reality works. The idea first gained traction when physicists studying black holes stumbled on a paradox. When matter falls into a black hole, what happens to the information it carries? Quantum mechanics says information can't be destroyed, but general relativity suggests it vanishes forever inside the singularity. The solution: maybe the information isn't lost, it's smeared across the black hole's event horizon, like a cosmic fingerprint preserved on its surface. This led theorists to a radical proposal. If a black hole's 3D interior can be described entirely by data on its 2D boundary, could the same be true for the entire universe? Think of it like a hologram you'd see on a credit card. The flat surface holds all the information needed to create a 3D image when light hits it just right. Similarly, the holographic principle suggests that the universe's true source code might live on a distant two-dimensional plane, with our reality as the projected illusion. Even stranger, this isn't just philosophy, it's testable. Scientists analyzing the cosmic microwave background, the afterglow of the Big Bang, have hunted for subtle pixelation or noise that might betray the universe's resolution limit, like a TV screen revealing its hidden dots when viewed up close. But why would the universe work this way? One answer lies in entropy, the measure of disorder. A black hole's entropy scales with its surface area, not its volume, hinting that all its information fits on its boundary. If the cosmos follows the same rules, then our 3D experience might just be the universe's way of unpacking data stored on an unimaginably vast 2D sheet. This could also solve another cosmic puzzle: why the universe appears fine-tuned for life. If reality is a projection, its laws might emerge from deeper, simpler rules encoded on that boundary, like how a video game's complex world runs on basic binary code. The implications are dizzying. If the holographic principle is true, then free will, time, even causality might be secondary features, emergent properties of a deeper, more alien reality. Your thoughts, memories, and emotions could be shadows cast by interactions on that distant surface, with no more substance than a character's feelings in a novel. Some versions of the theory even suggest that what we call space is just a network of entangled quantum bits, with every particle connected to others in a vast, invisible web. Yet the holographic universe isn't without critics. Some argue it's just a mathematical trick, a useful tool for solving black hole puzzles that shouldn't be taken literally. Others point out that no experiment has yet found definitive proof of pixelation or holographic noise in cosmic data. But supporters counter that future quantum gravity experiments or more precise measurements of the cosmic microwave background might finally reveal the universe's true, flat nature. Whether real or just a provocative metaphor, the holographic principle forces us to confront a humbling possibility. Reality as we know it might be the ultimate illusion, a shimmering mirage painted on the canvas of something far stranger. So the next time you gaze at the night sky, remember you might not be looking out into space, but inward at a reflection of data written on the edge of existence itself. Perpetual motion machines are supposed to be impossible, a fantasy that violates the sacred laws of thermodynamics. Yet in 2016, physicists created something that comes alarmingly close: time crystals, bizarre quantum structures that flip between states endlessly without any energy input. Picture a clock that ticks forever without winding, or a diamond that pulsates between shapes continuously at absolute zero. These aren't hypotheticals, they're real, lab-grown anomalies that rewrite what we thought matter could do. Time crystals defy everything classical physics taught us about equilibrium. Normal systems, when chilled to their lowest energy state, settle into stillness like a pendulum at rest. But time crystals, first theorized by Nobel laureate Frank Wilczek in 2012, do the unthinkable: they keep moving. Their atoms oscillate in a repeating pattern, not because they're powered externally, but because their quantum entanglement locks them into an eternal dance. It's as if you dropped a ball into a valley and instead of settling at the bottom, it kept rolling up the sides on its own forever. Creating these crystals required hacking quantum mechanics at its core. Researchers used chains of ytterbium atoms or nitrogen vacancy centers in diamonds, zapping them with precise laser pulses to induce a non-equilibrium state. The result, a structure that cycles between configurations at fixed intervals, like a cosmic metronome immune to entropy's grasp. Even weirder, time crystals don't sync with the laser's rhythm. They respond at a fraction of the frequency, a phenomenon called subharmonic oscillation. That's as unexpected as a guitar string vibrating at half the speed you pluck it. Why does this matter? Time crystals aren't just lab curiosities. They hint at entirely new phases of matter, ones that could revolutionize quantum computing. Imagine qubits protected from decoherence by their own perpetual motion, or fault-tolerant quantum memory that never needs refreshing. Some theories even suggest time crystals might model exotic physics like space-time loops or pre-Big Bang conditions, offering glimpses beyond our cosmic horizon. Of course, they're not perpetual motion machines in the classical sense. They don't output energy or defy thermodynamics. They just redistribute what's already there in mind-bending ways. But their very existence proves that matter, under the right quantum rules, can choreograph its own eternal rhythm. So while time crystals won't power your house or spin forever in the traditional sense, they've already accomplished something far more profound. They've shattered our assumptions about what's possible in the quantum realm, revealing a universe where even in absolute stillness, the dance of atoms never truly ends. What if the four dimensions we experience, length, width, height, and time, are just the surface of something far deeper? For decades, physicists have wrestled with a bizarre possibility. Space-time might be hiding extra dimensions curled up so tightly we can't perceive them. This isn't science fiction, it's string theory's bold proposal that reality could have 10 or even 11 dimensions, with the missing ones folded into microscopic loops or twisted geometries. Imagine observing a garden hose from a distance. From far away, it looks like a simple one-dimensional line, but up close, you realize it has a circular second dimension wrapped around its length. Now picture that same principle applied to the fabric of space-time itself, with 6 or 7 additional dimensions compressed into sizes smaller than an atom, so tiny they escape even our most powerful microscopes. One of the most compelling reasons to entertain this wild idea, gravity's puzzling weakness compared to other fundamental forces. Electromagnetism can make a simple fridge magnet defy Earth's entire gravitational pull, and the strong nuclear force binds protons together so tightly it outmuscles gravity by a factor of 1,000,000 trillion. If gravity's influence is leaking into these hidden dimensions, spreading its strength where we can't detect it, that could explain why it feels so faint in our four-dimensional experience. Think of it like water seeping through the pores of a sponge. What seems weak on the surface might just be diluted across unseen layers. The math behind these extra dimensions isn't just elegant, it's surprisingly robust. String theory, which posits that particles are actually vibrating strings, requires these additional dimensions to make the equations work. Without them, the theory collapses like a house of cards. Some models suggest these hidden dimensions could be Calabi-Yau manifolds, intricate 6-dimensional shapes resembling crumpled paper at scales 1,000,000,000 times smaller than an atom. Others propose they might be brains, short for membranes avast, higher dimensional surfaces where our universe is stuck like a painting on canvas, with gravity alone able to slip between the brushstrokes. Could we ever prove these dimensions exist? Experiments at the Large Hadron Collider have searched for telltale signs, like particles vanishing momentarily as they dip into hidden realms, or microscopic black holes blinking into existence. So far, no luck, but some physicists speculate that gravitational wave detectors might one day catch echoes of higher dimensional phenomena, like ripples from collisions happening in dimensions beyond our perception. Others suggest that precise measurements of gravity at microscopic scales could reveal deviations from Newton's inverse square law, a smoking gun for extra dimensions warping the force's behavior. The implications are staggering. If these dimensions exist, they could rewrite our understanding of everything from the birth of the universe to the nature of dark energy. A hidden dimension might even serve as the incubator for a baby universe budding off our own, potentially offering a mechanism for cosmic reproduction. Or they could explain the perplexing fine-tuning of our physical constants, with different dimensions selecting different laws of physics across a grand multiverse. For now, extra dimensions remain tantalizingly out of reach, dancing at the edges of our equations and experiments. But if they're real, they'd reveal a universe far more labyrinthine than we ever imagined. One where the fabric of reality isn't just stretched across 4 axes, but woven into secret folds beyond our sight. So the next time you drop a ball and watch it fall, ask yourself, is gravity truly weak or just diluted across dimensions we've yet to unfold? The answer might lie curled up in spaces smaller than a thought, waiting to be discovered. Your experience of now isn't just personal, it's physically unique to you, shaped by where you are and how fast you're moving. Think about the last time you video called someone halfway across the world. When they said hello, their voice didn't reach you instantly. It traveled through fiber optics at nearly light speed, introducing a tiny delay. For those milliseconds, your present wasn't perfectly synced with theirs. Now scale that up to cosmic proportions. If you're orbiting Earth on the International Space Station, your now diverges from mine on the ground by microseconds each day due to relativity's time dilation. And if you were cruising near a black hole, our shared moment could stretch into years or centuries apart. This isn't just about delays in communication. Einstein's relativity shattered the notion of a universal clock, revealing that simultaneity is an illusion. Imagine two lightning bolts striking a train track, one at the front, one at the back. To a bystander on the platform, they might appear simultaneous, but to a passenger zooming past on a train, the bolt nearer the front would seem to strike first because the light from it reaches their eyes sooner. Neither observer is wrong. Their nows are just framed by their own motion. Neuroscience complicates this further. Your brain doesn't process sensory input in real time. It constructs a cohesive present by stitching together signals that arrive at slightly different speeds. Touch, sound, and light all travel through neural pathways at varying rates, yet you perceive them as synchronized. Experiments show this temporal binding window can stretch or compress. When you clap your hands, your brain backdates the sound to match the visual of your palms meeting, even though the sound arrives milliseconds later. Your subjective present is a carefully crafted fiction, edited for coherence. The implications ripple across reality. GPS satellites must account for relativistic time differences to keep your maps accurate, but your brain has no such calibration. Two people in the same room can literally experience different sequences of events based on attention or expectation. In quantum experiments, particles seem to decide their states retroactively, blurring the line between past and present. Even consciousness itself might rely on this elastic now, a fleeting window where the brain integrates stimuli into a stable narrative. So the next time you say, right now, remember, your present is as unique as your fingerprint, woven from the threads of motion, gravity, and neural trickery. The universe has no master clock ticking for us all, just countless subjective moments, each as real and fleeting as the last. The universe might be sitting on a quantum time bomb, one that could rewrite the very laws of physics in an instant. This nightmare scenario is called vacuum decay, and it starts with a chilling possibility. What we think of as empty space might not be truly empty, but trapped in a fragile state known as a false vacuum. Picture a marble resting on the edge of a bowl. It seems stable, but the slightest nudge could send it tumbling into a deeper, more stable valley. Now imagine that bowl is the fabric of reality itself, and the marble is the universe's fundamental energy state. If our cosmos is perched in that precarious false vacuum, a single quantum fluctuation could tip it into the true vacuum, unleashing a cascade that erases the laws of physics as we know them. How would it happen? Somewhere in the universe, maybe in a distant galaxy, maybe right next to you, a tiny bubble of true vacuum could form. Inside this bubble, the rules change. Particles gain new masses, forces switch strengths, and the constants that govern reality shift irrevocably. Worse, this bubble would expand at light speed, its walls rewriting everything they touch. Planets, stars, even space-time itself would be overwritten before anyone could blink. There'd be no warning, no time to react, just an instant, inescapable transformation of reality. One moment you're sipping coffee, the next, the very atoms in your body no longer bind together because electromagnetism no longer works the way it did. The scariest part, this isn't just speculative doom-mongering. The standard model of particle physics allows for this possibility, and some measurements of the Higgs field, the energy field that gives particles mass, suggest our vacuum might indeed be metastable. It's held stable for 14 billion years, sure, but quantum physics doesn't care about streaks. given enough time or the right random fluctuation, the dice could roll against us. Yet there's a twist: vacuum decay isn't certain. Some theories suggest the universe might already be in its true, stable vacuum, making this apocalypse impossible. Others argue that even if we're in a false vacuum, the time required for spontaneous decay could exceed the current age of the universe by trillions of years. But here's the catch: if a high-energy particle collision in a lab or cosmic ray event artificially triggered the transition, the timer wouldn't matter. The bubble would still race outward, unstoppable. For now, vacuum decay remains a terrifying what-if lurking at the edge of physics, but it forces us to confront a humbling truth: the universe's laws might not be set in stone. They could be just as fragile as the quantum fields that underpin them, waiting for the slightest tremor to rewrite the cosmic rulebook, leaving no trace of the physics, the stars, or the life that came before. Time isn't just flexible, it might be an illusion altogether, at least in the quantum realm. Down at the smallest scales, where particles flicker in and out of existence and reality blurs into uncertainty, the steady tick of a clock could vanish entirely. Some theories, like loop quantum gravity, suggest time isn't fundamental at all. It's something that emerges from a deeper, timeless sea of quantum interactions, like the illusion of movement in a flipbook. Picture the universe as a vast network of interconnected nodes, like beads on an invisible string. In loop quantum gravity, these nodes represent tiny grains of space, the smallest possible bits of reality, far smaller than an atom. The connections between them aren't fixed, they shift and change, creating what we perceive as the passage of time. But here's the twist: at the most basic level, there's no clock ticking in the background. Time isn't a backdrop against which events unfold, it's a side effect, a story the universe tells itself to make sense of change. This idea turns everyday intuition on its head. We think of time as a river flowing in one direction, but at the quantum level, it might be more like a series of snapshots with no inherent order. Some physicists compare it to a movie reel where the frames could, in principle, be shuffled and still make sense. The sequence we experience, cause followed by effect, past leading to future, could be a macroscopic illusion, like how the smooth motion of a film emerges from static images projected fast enough. The implications are staggering. If time isn't fundamental, then the Big Bang wasn't necessarily the beginning of time, just a transition from one quantum state to another. The arrow of time, the reason we remember the past but not the future, might arise from the way quantum entanglements spread and complexify, like ink dispersing in water. Even black holes, those cosmic destroyers of time near their singularities, could be extreme examples of time dissolving back into its quantum roots. Experiments are already probing this radical idea. Quantum systems can exhibit behaviors where cause and effect blur, like particles seeming to retroactively change their states based on future measurements. Some interpretations of quantum mechanics, like the Wheeler-DeWitt equation, describe a universe frozen in an eternal now, with time as a phantom we construct from correlations between events. So next time you glance at a clock, consider this: the seconds ticking by might just be the universe's way of keeping score in a game where the rules are far stranger than they appear. Time as we know it could be a scaffold our brains built to navigate a reality that, at its core, operates outside it entirely. The shape of the universe isn't just about geometry, it could dictate how time itself unfolds on the grandest scales. Picture space as a giant sheet of paper. If it's perfectly flat and infinite, time might stretch endlessly forward into oblivion. But if the universe curves back on itself like a four-dimensional sphere, time could loop in ways that defy our everyday intuition, creating a cosmic cycle where endings birth new beginnings. A closed universe where space-time wraps around like the surface of a balloon opens the door to mind-bending possibilities. In this scenario, if you traveled far enough in one direction, you'd eventually return to your starting point, not just in space but in time. Some theories suggest such a universe could collapse back into a singularity in a big crunch, only to rebound in another big bang, resetting the cosmic clock. Time here wouldn't be a straight line but a circle, with each cycle rewriting the laws of physics anew. On the other hand, a flat or open universe, one that stretches infinitely without curving, paints a far lonelier portrait of time. With no closure, no crunch, time would march forward relentlessly until every star burns out and every black hole evaporates. Entropy would win, leaving the cosmos cold and empty, its history fading into an eternal silence. Then there's the wild card, a saddle-shaped open universe where space-time curves outward in a hyperbolic flare. Here, the expansion could accelerate so violently that not just galaxies, but atoms and even space-time itself would be torn apart in a big rip. Time in such a universe wouldn't just end, it would shatter, its final moments marked by the disintegration of causality itself. The most tantalizing question isn't just what shape the universe is, it's whether that shape dooms time to oblivion or grants it a second act. Right now, the evidence points toward a flat or nearly flat cosmos, but the margin of error leaves room for surprises. If future telescopes detect even slight curvature, it could rewrite our understanding of time's ultimate fate, not as a one-way street, but as a cosmic carousel, spinning through cycles of creation and destruction without end. Imagine dropping a feather and a bowling ball in a vacuum. They hit the ground at the same time, proving gravity treats all matter equally. But what if we replaced that bowling ball with its bizarre cosmic twin, antimatter? Here's where things get weird. According to Einstein, gravity warps space-time the same way for everything. Yet a handful of experiments like those at CERN Alpha collaboration hint that antimatter might not play by those rules. Some data suggests positrons and antiprotons could fall upward in a gravitational field, as if repelled by the very force that anchors our feet to the ground. If true, this wouldn't just tweak physics textbooks, it'd rip them apart. Antimatter is already the universe's ultimate doppelganger. Every particle has an antiparticle with opposite charge. Electrons have positrons, protons have antiprotons. When matter and antimatter meet, they annihilate in a flash of energy. But here's the puzzle: the Big Bang should have created equal amounts of both. Why is the universe made almost entirely of matter? One radical answer: antimatter doesn't just differ in charge, it might interact with gravity in reverse. Picture a world where your anti-self could step off a cliff and float skyward, defying everything we know about space-time's pull. Testing this isn't easy. Gravity's grip is weak compared to other forces, and antimatter is notoriously hard to corral. Even a speck of it touching normal matter triggers instant annihilation. But in 2023, CERN researchers trapped antihydrogen atoms in magnetic fields, watching their behavior in Earth's gravity. Initial results showed antimatter falling down, but with a margin of error that leaves room for surprises. Some theorists argue that if antimatter does repel gravity, it could have been ejected from the early universe, explaining matter's dominance. Others propose wilder ideas. Antimatter might fall toward negative mass, a concept that could enable warp drives or traversable wormholes if harnessed. The implications are staggering. If antimatter falls up, Einstein's equivalence principle, the bedrock of general relativity, would need rewriting. Space-time might not curve the same way for all objects, suggesting hidden dimensions or undiscovered forces. It could even hint at a mirror universe where physics is inverted, with antimatter stars and galaxies governed by anti-gravity. Until experiments like Alpha G or NAS, a planned antimatter gravity experiment, deliver definitive answers, this cosmic loophole remains tantalizingly open. So next time you drop your keys, consider this. Somewhere in the universe, their antimatter counterparts might be doing the exact opposite, floating into the void as if space-time itself were pushing them away. And if that's true, we're standing at the edge of a physics revolution, one that could redefine not just how objects fall, but how the very fabric of reality behaves under gravity's enigmatic sway. What if the universe isn't just something we observe, but something that responds to us? Beneath the equations of quantum mechanics lies a haunting question. Does consciousness itself play a role in shaping reality? At the quantum scale, particles exist in a blur of possibilities until measured, collapsing into definite states only when observed. This observer effect suggests something staggering, that the act of perception might not just record reality but influence it. Take the famous double-slit experiment, where electrons behave as waves when unobserved but snap into particle-like states the moment a detector clicks on. It's as if the universe hesitates, waiting for a conscious mind to dictate its next move. This idea spirals into panpsychism, the radical theory that consciousness isn't exclusive to brains but is a fundamental property of the cosmos, like mass or charge. Imagine electrons harboring whispers of experience, or stars possessing some dim awareness of their own glow. Far from mysticism, this emerges from a genuine scientific puzzle. How does subjective experience arise from inert matter? If consciousness is truly fundamental, then space-time itself might not be a static stage but a dynamic interplay between observer and observed, a cosmic dance where mind and matter co-create reality. Critics dismiss this as philosophy masquerading as physics, pointing out that observation in quantum mechanics simply refers to interaction with any system, not a conscious mind. Yet the line blurs in experiments like the quantum Zeno effect, where frequent observation freezes a system's evolution, as if reality requires our attention to keep unfolding. Some interpretations, like von Neumann-Wigner consciousness theory, go further, proposing that consciousness literally collapses quantum probabilities into concrete events. The implications rewrite our place in the cosmos. If consciousness molds space-time, then black holes might not just warp the fabric of reality, they could perceive it differently. Time's arrow could be less a law of physics and more a habit of collective observation. Even the Big Bang might reframe as a primordial act of cosmic attention, a singularity of awareness birthing space and time. Whether illusion or insight, this possibility forces us to confront a humbling truth. The universe might not just be stranger than we imagine, but stranger than we can imagine. And if consciousness is indeed woven into space-time's fabric, then every thought, every glance becomes a thread in the tapestry of reality itself. Time doesn't just pass, it's headed toward an inevitable expiration date. Whether the universe ends in fire, ice, or something far stranger, every possible cosmic finale shares one eerie feature: the dissolution of time itself. Take the heat-death scenario, where the universe expands forever, stretching space so thin that stars burn out, black holes evaporate, and matter itself decays into a lukewarm haze of photons drifting through an infinite void. In this frozen twilight, entropy maxes out, and without energy gradients, no hot or cold, no high or low change becomes impossible. Time, which relies on events unfolding, simply stops having any meaning. It's not that clocks wind down, it's that the very concept of before and after ceases to exist, like a movie reel where every frame fades to the same blank image. But heat-death isn't the only contender. The Big Crunch offers a dramatically different demise, one where gravity finally overpowers dark energy's expansion, yanking galaxies back together in a cosmic rewind. Space contracts, temperatures soar, and everything compresses toward a singularity. Yet here too, time faces oblivion. As matter nears infinite density, space-time curves so severely that the arrow of time bends into a loop, then snaps. Cause and effect implode, leaving the universe's final moments as indecipherable as trying to read a book reduced to ash mid-sentence. Then there's the Big Rip, a fate so violent it makes the crunch seem gentle. If dark energy grows stronger over time, it won't just push galaxies apart, it'll shred the fabric of reality itself. First planets, then atoms, then space-time's underlying structure tears apart. In this scenario, time doesn't fade, it's annihilated mid-tick like a clock shattered by a hammer. The last measurable instant would be a fraction of a second before total disintegration, where the very concept of duration becomes meaningless. But perhaps the most unsettling possibility isn't an end, but a transformation. Some theories suggest the universe could tunnel through quantum fluctuations into a new vacuum state, birthing a fresh cosmos with different physical laws. In this case, our timeline wouldn't conclude, it'd be overwritten, like a file deleted to make room for new data. Time as we know it would vanish, replaced by an alien chronology where beginnings and endings might not even apply. The common thread: time isn't an eternal backdrop, it's a contingent feature of our universe, as mortal as the stars. Whether frozen, crushed, or rewritten, its demise forces us to confront a paradox. The very force that gives our lives structure and meaning is on a cosmic scale, just a temporary glitch in the void. And that raises one final, haunting question. In a reality without time, could anything, even nothingness, still be said to exist? From black holes that stretch time like taffy to quantum particles that teleport across space, we've journeyed through some of the universe's most astonishing secrets, where gravity bends clocks, light defies time, and the vacuum of space itself boils with invisible energy. Think about that moment when you first realized your head literally ages faster than your feet, or that every star you see is a postcard from the past. Maybe your mind keeps circling back to the holographic universe theory, where all of reality might just be a two-dimensional projection, or the spine-tingling possibility that antimatter could fall up. But here's the wildest part: these aren't just abstract ideas, they shape your everyday life. GPS satellites correcting for time warps, quantum computers harnessing spooky entanglement, even the sunlight warming your skin, 8 minutes old by the time it reaches you, are all proof that space-time's weirdness isn't confined to textbooks. It's alive all around us, whispering that the universe is far stranger than our senses suggest. So which fact shattered your reality the most? Drop it in the comments. We're constantly diving deeper into these cosmic mysteries. And if your brain hasn't melted yet, hold on tight. What if everything we've covered is just the tip of the iceberg? What if space-time itself is merely the scaffolding for something even more unfathomable? Hit subscribe while you ponder that. We're just getting started. The universe still has vaults of secrets to crack, and you've got a front row seat. Until next time, keep looking up and questioning everything.